In this video, I would like to go over some of the mathematical rigor in the derivation of waves and the wave equation, a little bit more so than I was able to do during the lecture period. And we're going to start with the formal mathematical description of a wave. I will remind you that a wave is not necessarily sinusoidal, nor is it even necessarily periodic. A wave can have any form that represents a spatial distribution that propagates in time. And so in the most general sense, we can write a description of the wave by starting with y equals fx. And we have pictured over here some irregular shaped function that is a function of y as a function of x. Is equal to the variable y as a function of x. Now, as you hopefully recall from pre-calculus, if you have a function y equals f of x, if you were to plot y equals f of x minus a, it will take that function and it will translate it to the right. So plotting the above function, but where the argument is now f of x minus a, shifts this shape, which had its peak at roughly 0, it gets shifted now to location a on the x-axis. It is moved to the right. Now, given that a wave is a functional form that propagates with a velocity over some time, we can rewrite this using the relationship that a, the amount we shift this wave by, is equal to the v, the velocity of the wave, times t, time. That being the case, we can take this functional form and rewrite it as f of x minus vt, where we have this functional shape f of x that is shifted by a distance vt as time progresses. Given that functional form, we can now derive the wave equation, which is the differential equation describing all solutions that we call waves. Now, this is not only a differential equation, but it is also a partial differential equation, meaning that we will be taking derivatives in different variables, in two different variables, the partial derivatives with respect to time and to space. So again, as you recall from the last slide, the general form for a wave is a function of the form y equals f of x minus vt. And we're going to do something known in calculus as a substitution. We're going to define a new variable u that is equal to the argument of f, x minus vt. And now we're going to break out some calculus. So the first thing we're going to do is we're going to take the derivative of y, the partial derivative of y with respect to t. And the product rule teaches us that that can be rewritten as the derivative of this function with respect to u times the derivative of u with respect to t. And the partial derivative of u with respect to t is just negative v. So we end up getting that the del y del t, the partial derivative of y with respect to time, is equal to negative v times del f del u. Similarly, we can take the x derivative, and we get that the del y del x is equal to del f del u times del u del x. And the derivative of u with respect to x is just 1. So we end up getting that the partial derivative of y with respect to x is equal to the partial derivative of f with respect to u. We can also take the second derivative of both of these with respect to time and space. On this side, we take the second derivative with respect to time. We get another factor of v, of negative v, so that we end up getting that the second derivative of y with respect to time is equal to v squared times the second derivative of f with respect to u. And taking the second derivative with respect to x, we get that the second derivative of y with respect to x is equal to the second derivative of f with respect to u. And you'll notice that this is the same second derivative shown here, and so we can do a substitution, taking the second derivative of y with respect to x and just substituting it into here, and we end up getting this differential equation that relates the second derivative of y with respect to time to the same to the derivative, the second derivative with respect to x of the same variable y, or the same function y, multiplied by a constant v squared. And with just a little bit of rewriting, this gives us the form of the wave equation. So the wave equation takes a variable y, or an observable y, that has both a time and a space dependence, and any solution, any valid wave is a function that satisfies the condition that taking its second derivative and with respect to x and subtracting its second derivative with respect to time multiplied by 1 over its velocity squared gives us 0. That those two, that's the connection between the second derivative in space and time. Now, this is a very general equation, and there are lots of different solutions and different kinds of solutions. And just as with the harmonic oscillator, we can basically use this equation in a lot of different contexts. But what we're going to do is in each of those contexts, we can find a way to derive this equation, and then we can relate this 1 over v squared term to constants that are relative to that particular problem. And you'll see what I mean in the following slides. We're now going to talk a bit about wave speed. This is a photograph from back in the day for me, my postdoc project. We were working on ultra-fast photodetectors that could measure the wave speed of light itself, which is very impressive. In this picture, Mathieu is holding a flashlight, and he's going to shine the light into Preston's glove. Preston, by the way, is a graduate of ISU. He was a senior here in this picture. He's now the head of an Air Force research lab, so I think we do very well by our students here at ISU. Bernard is holding a stopwatch, and I'm going to record the time it takes the light to travel. One of the things that's impressive is that the photodetectors we developed that are now commercially available are actually better able, or they can measure the speed of light much faster than this picture would suggest. They measure the time it takes light to travel just a few millimeters. So let's talk about deriving wave speed. We're going to start with a very specific type of problem. As I said, the wave equations can be applied in a very general sense, but we're going to look at a very specific problem, and we're going to look at the derivation of the speed of a transverse wave. So the setup is we have a pulse that's traveling in the x direction on a string, and that string has some mass per unit length, mu. So this is the length density, as we call it. It's kilograms per meter are the units. And also that this string is under a uniform tension, and we're going to use F to represent that tension force. And we want to know what is the speed of the pulse. So let's take that pulse on the string, and we're going to consider a small segment of that string. And the mass of this segment is going to, delta m, is going to be equal to the length of the piece of string, delta x, times its linear density, mu. So that's the relationship there. And now we're going to think about, what does this little tiny mass do? Well, this is a transverse wave. So what this mass does is it goes up and down. And so we're going to be looking at how this goes up and down, and we're going to actually be leveraging Newton's second law, which is to say F equals ma. And we have our m, it's delta m, and we know that the acceleration is going to be purely in the y direction. There's no acceleration of this in the x direction, since this is a transverse wave. So we can take a look at this little segment of string, and we know that we've got forces. One force is pulling this way, one force is pulling this way. And we know that the x components have to balance out, since this little string is only going up and down, it's not going left and right. That means that F1, the force at this point versus F2 at this point, F1 of x equals F2 of x, because they must balance if there's no acceleration in this direction. A sub x is equal to 0. Furthermore, f of x must be also be equal to the tension in the string when there is no wave at all. So F1 of x equals F2 of x equals F. Now what about the y components? Well, the f components cancel, but it's clear that the y components don't, because after all, this segment of the string is going up and down. And so we can actually relate the component forces at the two ends of this string to the slope of the string, and we have that the F1 of the y component of F1, and the force applied here, divided by the total tension of the string, is going to be equal to the derivative of y with respect to x evaluated at point x. So this is the slope. And then F2 of y, the y component at point 2 is divided by f is equal to del y del x, the slope, the instantaneous slope here, evaluated at x plus delta x. So these equations we now have under our belt, and we know that the net force on this is going to be equal to F2 of y minus F1 of y. That's the net force applied to this. And using this relationship here, we can write that that's equal to F times the derivative of y with the partial derivative of y with respect to x evaluated at x plus delta x minus the partial derivative of y with respect to x evaluated at x. And this, of course, to formulate it in terms of Newton's second law, the net force is equal to ma. And again, the delta mass is just equal to the linear density times the little delta of the length of the string. And acceleration, by definition, is the second derivative of y with respect to time. Well, now we can write this as being equal to this term, and we get the following relationship here. And we're going to do a couple calculus tricks that hopefully you remember from your calculus class. We're going to divide the delta x over to this side of the equation. And so we now have del y del x evaluated at x plus delta x minus del y del x divided by x, or evaluated at x divided by delta x. And we can take the limit as that delta x in both of these locations goes to 0. Well, this is the definition of a derivative. And so we are taking a partial derivative with respect to x of del y del x, and which is to say that we are coming up with the second derivative. This is the second derivative of y with respect to x. And that's equal to mu over f times the second derivative of y with respect to time. At this point, your eyes should immediately recognize the pattern. We have actually shown that the motion of this little segment of string is consistent with the wave equation. And in that consistency, the term mu over f corresponds to the 1 over v squared term, which means that v in the case of a string vibrating is equal to the square root of the tension of the string divided by the mass density of the string. And there we have it. Another example we can look at are pressure and density oscillations, in other words, sound. So in the following slides, we are going to go through and try to understand the speed of sound. Now, before we do, we need to kind of understand pressure and density oscillations. So when we have gas at equilibrium, the pressure and density of that gas are uniform. A sound wave, as you recall, is a periodic longitudinal oscillation of the particles in the gas. So at any moment in time, a particle in the gas can move forward in the direction that the wave is propagating, or backwards in the direction that the wave is propagating. Again, this is longitudinal, but it's just going to vibrate about that point. The particle itself is not going to have any motion, net motion in any direction. So let's consider one slice of air. Oscillation to the right causes pressure to increase. That increase in force causes neighboring air to be displaced forward. And so, you can kind of think of like there's a line of people and somebody runs into the back of the line, and that knocks the person in front of them into the person in front of them into the person in front of them, and that is a wave. Those collisions propagate forward, but the people themselves, after they lunge forward, they correct themselves and move back again. So there's a compression and a relaxation, but the impact sort of propagates forward. And what you end up getting is a slice of air that oscillates back to a region of low pressure. So first it oscillates to high pressure, then it oscillates back to low pressure. These small volumes of air do not propagate with the wave. They only oscillate around their equilibrium position. As I said, there's no net motion of the column of air. It just vibrates forward and backwards, where forward and backwards means in the direction of propagation and away from the direction of propagation of the wave. Now we can plot this for harmonic longitudinal waves. So consider gas in a long, thin horizontal tube. Each particle of gas oscillates horizontal in a harmonic way. Now, this graph is showing the longitudinal displacement, but it's a little bit confusing because we're showing it using a transverse direction. So even though this wave looks like a transverse wave, bear in mind that what this means to say is that a particle of air that belongs at point equals 0 is actually displaced forward by 10 micrometers at this location, and another point of air right here is 10 micrometers back from where it should be. So all of these S's represent motion in the direction of the waves. So plus 10 and minus 10, plus 10, minus 10. So all of the points are vibrating like so, and this is pictured by the sinusoid. And you'll remember from our earlier lectures that the form of it is this displacement function, S of x and t, which is equal to an amplitude, S max, times the cosine of kx, where k is the wave number, minus omega t, where omega is the angular frequency. Again, air normally at x0 is displaced to the right by 10 micrometers, and here air normally at 50 centimeters is displaced to the left by 10 micrometers. So this is the displacement function, and there's a couple things that we can observe about this. All of the air between here and here is to the right of where it should be, and all of the air between here and here is to the left of where it should be. So this air is all to the left, this air is all to the right. It stands to reason that at this point in the middle, there would be compression, there would be higher pressure, because all of the air particles over here are to the right of where they should be, and all the air particles here are to the left of where they should be. Similarly, at this point, we expect low pressure, because at this point, all of these air particles are to the right, and all of these air particles are to the left. There's a stretching effect. And at these points where they're pressing against each other, we have regions where there's an accumulation and a higher pressure. This all boils down to a phase difference. As you might have observed, so the displacement function is described by a cosine, but you might have observed that the pressure function was maximum when the displacement function was 0. And so this corresponds to a sine wave, which has a phase difference. Now, I want to bring to your attention that when we're talking about the pressure here, we're talking about the gauge pressure. No matter what in this problem, there is an ambient air pressure of 1 atmosphere. But where the air is compressed, that pressure is a little bit higher than an atmosphere, and where the air is stretched out, that pressure is a little bit lower. So the gauge pressure, P, the total pressure, P, is equal to atmospheric pressure plus the gauge pressure. That is what this function is describing. Note that the density is in phase with the pressure, and that should make sense. Where you have a higher pressure, you have a higher density. Where you have a lower pressure, you have a lower density. And again, you can define density oscillations as being fluctuations around the nominal air density. This is a top hat problem we didn't get to in class, but it's a nice illustrative example of a dust particle in front of a speaker. When you turn on the speaker, the dust particle will either A, oscillate back and forth horizontally, slowly moving to the right, it will steadily move to the right, or it will oscillate back and forth horizontally. Take a moment to think of the answer. If you need to, feel free to pause. Otherwise, I'm going to move forward now. So the answer is that it oscillates back and forth horizontally, and I've already said this. In our example of a line of people where one person bumps into one person, bumps into the other, as soon as they lunge forward, they overcorrect and go backwards. No person goes forward, but that impact of the initial group of people colliding into each other propagates forward. So each individual parcel of air is going back and forth, and the one in front of it is going back and forth, and the one in front of it is going back and forth. And they're all oscillating, and that back and forth motion is propagating along, but no particle has a net motion, and the dust is following its parcel of air, so it's just vibrating back and forth. So this is what the motion of the dust particle might look like. Now that we understand the concept of these pressure longitudinal waves, we can work on deriving the speed of sound. So let's consider a pipe with a cross-sectional area of A, and it's filled with air. And now what we're going to do is, much like with the string, we're going to look at a small element that has a thickness of delta x, and it's located at position x. This is what that parcel looks like in equilibrium. On either side, it has nominal atmospheric pressure, and it's balanced. But due to due to a wave, this element is going to move, and it's going to change its size. So it's going to move from x to x plus s, where s is the displacement, and its size is going to change to delta x, its initial size, plus delta s. And on either side of it, it's going to see different pressures. On the left, it sees the nominal atmospheric pressure plus P1, and on the right, it sees the nominal atmospheric pressure plus P2. Now, before we move on, we need to define a new concept, and this is what's known as the bulk modulus. The bulk modulus is a property of materials, particularly here we're talking about gases, and it's sort of a restorative force for gases. If you scrunch a gas together, it'll kind of push its way out. And the bulk modulus is defined as the gauge pressure, negative of the gauge pressure, divided by the fractional change in volume, delta V divided by V. That's the bulk modulus. Now, as you'll recall, the volume of this parcel of air is equal to the cross-sectional area times delta x. That gives you the volume of, say, the cylinder. And then delta V, the change in the volume, is going to be equal to the cross-sectional area times delta S, which is the change in the length of that little parcel of air. We can now write delta V over V as being A delta S divided by A delta X, which reduces to delta X over delta S over delta X. And we can take the limit as delta X goes to 0, and we get that delta V over V is just equal to the derivative of the displacement with respect to position X. And now we can take this relationship, rewrite it as the gauge pressure equals B times delta V over V, which is equal to negative B times del S over del X, the first derivative of S with respect to X. Now, if we take the harmonic case where S is a cosine function, it becomes immediately apparent why we have the phase shift between pressure and displacement, because remember, pressure is related to displacement by a derivative, and if we take the derivative of this function, we get a sine, and the derivative with respect to x will bring that k value out of the equation, and so we will get, and then we also have that factor of b, so we will get that the pressure is equal to bks max. This is the maximum pressure, gauge pressure, times a sine. So the displacement's a cosine, the pressure is a sine, out of phase as predicted. So now let's derive the speed of the longitudinal wave. We're going to operate almost exactly the way that we did with the guitar string, which is to say that we're going to show that we can derive that the behavior of this is consistent with the wave equation, and then when it is, we're going to show that the various constants map to that 1 over v squared, and that relationship is going to tell us how to determine the speed of sound in air. So as you recall, the pressure on either side of the parcel due to the wave is imbalanced now. On the left it's P0 plus P1, and on the right it's P0 plus P2. The parcel has shifted by some displacement, and the length of the parcel is now delta x plus delta s. So what is the net force element on this parcel? We are again going to basically set up F equals ma. But what is the F? Well, F is going to be the pressure difference between this side and this side. The P0s cancel, but we get that the pressure difference is P2 minus P1. And if you multiply pressure by cross-sectional area, that gives you force. So the net force on this little parcel of air is going to be P1 minus P2 times A. What's the acceleration of the element? Well, that's just the second derivative of the displacement with respect to time. That's just the definition of acceleration. And what's the mass of the element? Well, it's going to be the density of the air times the cross-sectional area times delta x. This is just the volume times the density, and that gives us our delta m. So now we can write out F equals ma. F equals ma. Okay? So now we can use that calculus derivative trick, and we can divide this delta x over to this side, and then we can shrink delta x. And as delta x goes to 0, this turns into the derivative of pressure with respect to x. So we end up getting negative del p del x equals rho times the second derivative of s with respect to time. Yeah. And that minus sign, by the way, is because this should be P2 minus P1, so it's actually a negative of the derivative. So now we're very close to having our wave equation, so stay tuned for the next slide. As we'd already derived, pressure is equal to negative B times del S del X, and we have this relationship that negative del P del X is equal to the density times the second derivative of S with respect to time. This we derived from F equals ma, and this we derived from the definition of the bulk modulus. And we can take the derivative of this, which will give us another way of writing del P del X, and we find that that's equal to negative B times the second derivative of S with respect to S. At this point, we're ready to do a substitution because we can just substitute this right into this term. And when we do that, we end up getting that the density times the second derivative of S with respect to time is equal to the bulk modulus times the second derivative of S with respect to x. And we immediately recognize that this is the wave equation, where this time, instead of 1 over v squared, we have negative rho over b. And that means that the velocity must be equal to the square root of b divided by rho. So it's the square root of the bulk modulus, which is sort of a measure of the restoring ability of the air, the resistance of the air, the pushback of the air to being compressed, divided by its volumetric mass density. And this really brings us to sort of the general picture of what the anatomy of the velocity of a wave looks like. It's in the form of the square root of some restoring force property. In the case of the string, it's the tension. In the case of air, it's the bulk modulus, divided by an inertial property, which is sort of how much inertial stuff there is per unit of the space in which that wave is propagating. In a string, which is one-dimensional, where the wave is propagating, on a single line, we care about the line mass density, the linear mass density, whereas for sound, which is a three-dimensional phenomenon, we care about the volumetric mass density. And so we have, for a string, v is equal to the square root of f over mu. And you can do an example for a rope or wire. You might have 1,000 newtons of tension and a mass density of 0.05 kilograms per meter. That would give you a speed of 140 meters per second. So that just kind of gives you a sense of the magnitude of speed of vibrations on a rope or wire. Sound in a fluid is, again, v equals b over rho, square root of b over rho. And to plug in, for example, the parameters for water, what we end up getting is that the speed of sound in water is about 1480 meters per second. And in a solid, instead of the bulk modulus, we use something called Young's modulus. And so for steel, if we calculate it, sound travels at 5,060 meters per second, which is quite fast. This is another top hat problem, a cool one that we didn't have a chance to do in class. A large munitions factory and a town are separated by a rocky hill at a horizontal distance of about 5 kilometers. An accident produces a huge explosion in the middle of the night. What do the town folks experience? Either A, first the room shakes, then they hear the explosion. B, they hear the explosion first, and then the room shakes. Or C, they hear an explosion and the room shakes at the same time. Take a moment to think about this problem. If you need more time, feel free to pause here, but I'm going to go on right now. The answer is that the room shakes first and then they hear the explosion. Let's take a look at this. Let's say that there's an explosion 5 kilometers away, there's a hill. The vibrations, the physical mechanical vibrations, are going to be propagating not through air, but through the rock, through the granite of, let's say, this hill or this mountain. And if we calculate the time that it takes, then we have to divide the distance, 5 kilometers, by the speed of sound in a solid. For granite, that's about 6,000 meters per second, and we get that it only takes about 0.8 seconds for the vibrations from the explosion to reach the house. The sound traveling through air, on the other hand, the speed of sound in air is only 343 meters per second. And so to traverse 5 kilometers, and in fact it probably even has to go a little further to get sort of around the hill, the sound would take at least 14.6 seconds to reach the house. This actually happened in California during World War II, where there was a munitions factory that blew up overnight. Most people woke up distressed to a light quake. Then, on the order of tens of seconds later, they heard the explosion. Many people attributed this to a sixth sense, but in fact, what had really happened was just the laws of wave propagation, that the vibrations woke them up, having arrived first, traveling through solid ground, much faster than the sound. And with that, that's the end of these slides. Thank you. I hope this was helpful, and good luck on your upcoming exam.